In the last video, we introduced the concept of force and provided some basic idea of how forces work. In this video, we will introduce several different types of forces and use Newton's second law to relate them to acceleration. To keep things simple, the forces in this video will point either in the x direction or in the y direction. We will use a simple example of a rocket to illustrate the process of solving force puzzles. It's a little different from the process for kinematics puzzles. Consider this puzzle. A 200 kilogram rocket is initially standing still. Its thrusters will provide a force of 500 newtons. What acceleration results? The first step of this puzzle is our usual drawing of a picture, same as in kinematics. Here is our rocket. But the second step is different from kinematics. We don't need to take two photos. That's because in force puzzles, we're generally either solving for an unknown acceleration, as in this case, or an unknown force. Both are quantities that usually stay constant within a forces puzzle. Instead, we draw a second picture known as a free body diagram. This is a way of cataloging the forces that occur on an object. In a free body diagram, we represent the object as a spot and draw one arrow to represent each force vector. The size of the arrow is proportional to the strength of the force, and the direction of the arrow is the same as the direction of the force. We label each arrow with the type of force that's acting. In this generic case, where the rocket's thruster is applying the force, we call the force an applied force and label it F sub A. The third step is the same as before, setting the origin and axes. We always set the origin and axes on the free body diagram. We always set the origin on the spot. However, we can choose which way we want to be positive. In this case, we will set rightwards as positive. The fourth step is to find the total force in each direction. Here, there's only one force acting on the rocket, the applied force, and it's in the x direction. So we say the total force in the x direction is composed of just one force, the applied force. But now, look at Newton's second law. Total force equals mass times acceleration. So we can substitute the applied force in to get applied force equals mass times acceleration. Step 5 is to set the total force from step 4 equal to mass times acceleration. Step 6 is to substitute all the known information into the equation from step 5. Here, we know the applied force, 500 I hat newtons, the way we've drawn it, and the mass, 200 kilograms. Step 7 is to solve for the unknown. The acceleration is unknown, and we just need to divide both sides by 200 kilograms to solve for the acceleration. The acceleration is 2.5 I hat meters per second squared. This is the process for solving all force puzzles. It's similar but not identical to kinematics puzzles. The steps are: 1. Draw a picture. 2. Draw a free body diagram. 3. Set origin and axes. 4. Find the total force in the x direction and in the y direction separately. 5. Use Newton's second law to set total force in each direction equal to mass times acceleration in that direction. 6. Substitute for the knowns. And 7. Solve for the unknown. An applied force is the generic name for any push or pull that an object experiences. But some forces have different names. For instance, if something is pulled on a rope, we say the object experiences a tension force. There's no real difference between a tension force and an applied force. It's just that a tension force always comes through a rope or a cable or a string. Consider this question. A 20-kilogram asteroid is initially standing still. A cable is attached to it and starts pulling. The asteroid accelerates at 0.75 meters per second squared. What is the tension in the cable? Let's start by drawing our usual picture of the situation. Here's an asteroid, and let us say that here is a claw, and here is the cable, which is going to drag it, let's say towards a rocket which is sitting here or something like that. Now, remember that we're doing this from the asteroid's point of view. The asteroid has a mass of 20 kilograms. And if we were to draw its free body diagram, we would say that it has, first of all, we represent the asteroid as a spot. It has only one force acting on it, and that is the pull from this cable. Now, there is no functional difference between a pull from a cable and a push coming from something like the thrusters on a rocket, right? So we can treat this new pull in the same way. It just so happens we have a difference in terminology. A pull from a cable is called a tension force, whereas a push coming from anything else would have been called an applied force. The two forces work the same way, it's just that we have a difference in terminology. Whenever there's a rope involved, we call it a tension force. That being done, let's now draw what the axes ought to look like. We have only one force, so to keep things simple, we're going to set the x-axis to be in line with that force. The origin in a force question always goes on the object, and we always draw it on the free body diagram itself. So to keep things simple, we're going to set the x-axis, positive x-axis, to be in line with this tension force. Now, next what we're going to do is we're going to apply F equals ma. But before we can do that, we need to evaluate what the total force is. There's only one force acting, and that force is acting in the x direction. So the total force in the x direction is equal to the tension force. But total force is also equal to mass times acceleration. So that means that the tension force is equal to mass times acceleration. The acceleration, we were told, was 0.75 meters per second squared. And we were looking for the size of the tension force. So the mass is 20 kilograms. The acceleration is 0.75 meters per second squared. So 20 times 0.75, that'll give us 15 newtons. And because force is a vector, it has to point in the same direction as the acceleration, or more correctly, the net force has to point in the same direction as the acceleration. So since the acceleration is in x, the net force must also be in x, and since the net force only consists of one force, that is the tension also points in x. So we could correctly call this 15 I hat newtons, and that is the size of the tension force that is acting on this asteroid. So far we've seen cases where something is subjected to only one force, but there can be multiple forces acting simultaneously. Consider this case. A 40-kilogram asteroid is initially standing still. Two cables are attached to it. They both pull leftward. One cable has a tension of 30 newtons. The other cable has a tension of 50 newtons. What is the acceleration of the asteroid? In this question, we have a 40-kilogram asteroid, and it is being drawn on two cables, something like that. Because there are two cables, each one of those cables has to have its own tension. Let's call this one T1, which we said was 30 newtons, and this one T2, which we said was 50 newtons. Now we are ready to draw our free body diagram. We use a spot to represent the asteroid, and we have our first tension pointed to the left, kind of like this, and our second tension also pointing to the left, like that. The next step is to draw our axes. The simplest way to do it is to have the origin, as usual, set where the spot is on our free body diagram, and in this case, to set x, positive x, as being leftwards. We are now ready to start analyzing the forces that are there in the x direction. In the x direction, the total force is T1 plus T2. But we also know that total force is equal to mass times acceleration in the x direction. So that means that T1 plus T2 has got to be equal to mass times acceleration. So T1 is 30 I hat newtons plus T2, which is 50 I hat newtons, all of which works out to the mass, 40, multiplied by the acceleration, which is the unknown. So 30 plus 50 is 80 I hat, is equal to 40 times the acceleration. Divide both sides by 40, and we get an acceleration of 80 divided by 40 is equal to 2 I hat meters per second square. So this is an example where we had two forces that were both pointed in the same direction. Forces are vectors, which means the directions of the pull matter. It makes a huge difference whether two different forces are pulling in the same direction or in opposite directions. For instance, take a look at this question. A 40-kilogram asteroid is initially standing still. One cable pulls the asteroid rightwards with 50 newtons of force. The other pulls it leftward with 30 newtons of force, that is, the opposite direction. What is the acceleration of the asteroid? In this case, we have the same asteroid, 40 kilograms, but this time we have the hooks on two opposite sides, and the cables likewise on two opposite sides. We have this tension over here and this tension over here. So this tension would be pulling it this way, this tension would be pulling it that way. So what are the two forces involved here? Well, there's two tensions, so when we draw out our free body diagram, we reduce the asteroid to a spot. We have one tension pointed like so, that would be T1, and the other tension pointed like so. We'd call that T2. I'm going to set my axes as follows. The origin, as always, goes on the asteroid itself, the spot in the free body diagram. I will set rightwards as being positive. So now we have to work out what the total force is going to be. So the total force we have to be careful about now, because the total force is being contributed to by two different tensions, but now they're in opposite directions. So there are two different ways of interpreting this. You could write it as being T1 plus T2, but keeping in mind the fact that T2 is negative, or you could write it as T1 minus absolute value of T2. I think that way is more confusing, so I'm just going to write it like this, and then I'm going to substitute negative values for T2 where it's appropriate. So again, this is the total force, and the total force is equal to the mass times the acceleration. So let's plug this all in. T1 plus T2 is equal to mass times acceleration. we were told that T1 is equal to 50 I hat newtons, and T2 is equal to negative 30 I hat newtons because it's pointed in the negative direction. And all of that is equal to a mass of 40 times an acceleration which is unknown. So 50 plus negative 30 is going to give us positive 20 I hat newtons, is equal to 40 times the acceleration, and therefore the acceleration is divided both sides by 40, and you get 0.5 I hat meters per second squared. So that's the acceleration. And we notice that it's positive, which means that the acceleration is going to be rightwards, which makes sense because T1 was the stronger force and T2 was the weaker force. Why exactly you would have a situation where you're pulling an asteroid with two cables in opposite directions, I don't know. But we're using our imaginations here. Point is, T1, being the stronger force, will overpower T2, so this will move to the right, but it won't accelerate as quickly as if T1 had just been operating by itself, let alone if T2 had been pointed in the same direction. That last question might have you wondering, if you had two forces that were pointed in opposite directions and they were exactly equal in strength, what would happen? Consider this question. A 40-kilogram asteroid is initially standing still. One cable pulls the asteroid rightwards with 50 newtons of force. The other pulls it leftward with 50 newtons of force. What is the acceleration of the asteroid? This may be a question where you've probably guessed the answer before we even start doing it. We have one tension which is pointed rightwards at 50 newtons and a second tension that is pointed leftwards at 50 newtons. So when you draw out the free body diagram, you are going to have one force pointed to the right, that's T1, and one force pointed to the left, that's T2. We will set our axes in the usual way. I'm going to put my origin at the center point, that is corresponding to our object. And our x-axis, we shall have point rightwards. Now, the total force in x is going to be T1, which is pointing rightwards, plus T2, which is pointing leftwards. So T2 is going to have a negative value, whereas T1 would have a positive one. Because positive is the rightwards direction, that's the direction T1 is pointing in, T2 is pointing in the negative direction, so T2 is going to have a negative value. And again, the total force is equal to mass times acceleration. So T1 plus T2 is equal to mass times acceleration. So if T1 is 50 I hat newtons and T2 is negative 50 I hat newtons, and all of that's equal to a mass of 40 times an acceleration, which is unknown, 50 and negative 50, obviously those cancel out, so you end up with a force of 0 is equal to 40 times acceleration, so the acceleration of this asteroid is 0. In other words, if it started off not moving, it will continue not to move. And if it started off with a certain velocity, it will continue moving but with that velocity in a straight line without a change in direction at a constant speed. Because if the forces perfectly balance each other out, then Newton's first and Newton's second both say the acceleration will be 0. It can move, but it can't accelerate. In this video, we discussed the procedure for solving all force puzzles. We're going to expand this procedure out as we start looking at forces in multiple directions, x and y, and even more complex questions than that.